We're going to spend some time looking at a handful more examples of just setting up ice tables, not getting into the algebra, just working with the ice table part. Consider the following reaction. 2SO2 plus O2 becomes 2SO3. Set up an ice table for the following initial mixture of reactants and products. I've got 1.0 molar SO2 and O2.
All right, so we just want to set up an ice table here. We're not going to worry about the algebra step afterwards here. Just trying to get the ice table set up. So the initial, the change, and the equilibrium. And so if I'm going to set up an ice table, I'm going to start with the reaction. So 2SO2 gas plus O2 gas in equilibrium with 2SO3 gas. So I got I, C. So for initial, you can see I'm told it's 1.0 molar SO2, 1.0 molar O2. Because I don't have any value given for SO3, I can just say that's a 0. Basically, I didn't mix that in this initial mixture. So now for the change, I'm going to have two parts. I'm going to have first, I want to figure out the direction. So when I'm figuring out direction, I want to look for anywhere there's a 0. If there is a 0, the reaction has to shift to that side because you can't get a negative concentration. So what we can do is we know that the products has to be a positive. We have to shift the products. That concentration has to increase. These concentrations, because they're on the other side, have to both decrease. So we can just figure out the sign of our expression. So now in terms of, we always know it's going to be x, and then we use just the coefficients. So basically for every 2 moles of this that reacts, there's going to be 1 mole of this that reacts, and 2 moles of this that are produced. You can just take the coefficients and bring them down. 2, we don't write a 1, we don't write a 1, 2, 2. And then we're combining all of this together. 1 minus 2x, 1 minus x, and 2x. So this would be the ice table that is set up. We're good to go. We could take this, at this point in time, this is really all we wanted for setting up an ice table. But what we could do with this is we could take it and plug it into Kc is going to be SO3 squared, SO2 squared, O2 to the first power. We can plug this stuff in. So 2x squared over SO2 is 1 minus 2x squared times 1 minus x. So we're not going to solve this one. That's not a pleasant algebra problem. Plus, we don't have a value for Kc. But we could certainly go through this process, do potentially long or tedious algebra, but we could figure out our concentrations at equilibrium.
Participation 220, question 1. Consider the following reaction. 2SO2 gas plus O2 gas yields 2SO3 gas. What is the E entry for SO3 in the ice table for the following initial mixture of reactants and products? It's 1.0 molar SO2 and SO3. This is the first question on participation 220, due Friday, February 20th at 11:59 p.m. over on Blackboard. Link to the assignment is right below the links to these videos. Again, consider the following reaction. 2 sulfur dioxide plus oxygen makes 2 sulfur trioxide. What is the E entry for SO3 in the ice table for the following initial mixture of reactants? It's 1.0 molar SO2 and it's 1.0 molar SO3. So 1.0 molar concentration for each of those. In general, when we're working with ice tables, we always want to hope for directionality's sake, for predicting direction, that there is something that's missing, because we can use that. We just know that it has to shift to the side of anything that's missing, but we don't always have that possibility. Let's look at an example. 2NO2 plus 7H2 becomes 2NH3 plus 4H2O. Pretty serious reaction. A mixture is prepared with all reactants and products at 2.0 molar
and Kc equals 623. Set up an ice table to describe the shift to equilibrium.
All right, so once again, we are looking to just set up ice tables. Okay, it's going to tell us our shift to the equilibrium. We have just an initial mixture. So I'm going to start by writing out my reaction. So it'd be 2NO2 gas plus 7 H2 gas is in equilibrium with 2NH3 gas plus my waters. Initially, everything is at 2. So previously, we've just looked for zeros. Wherever there's a zero, you got to shift to that side of the reaction. But here we don't have any zeros, so we can't use that. So we need to figure out direction of shift. So in order to figure out direction of shift, what we can do is we can compute Q. We know that it's going to be the concentration of NH3 squared, concentration of H2O to the 4th, concentration of NO2 squared, concentration of H2 to the 7th. Plug them in, plug in our 2's. We get 1/8. So QC is 1/8, 0.125. QC is 623. This is less than that, 0.125. So because QC is less than KC, that's going to be a shift to products. So if I'm going to have a shift to products, that means this, positive on my product side, negative on my reactant side. So now I've got the direction. I know for the amount, I just take the coefficient 2x, 7x, 2x, 4x. And I can combine 2 minus 2x, 2 minus 7x, 2 plus 2x, 2 plus 4x. And this is a very unpleasant algebra problem, so we are not going to worry about it. But if you plug that, you could plug that in to similar to this for your KC expression. It'd be all those, that 7th exponent is going to be plenty not fun to deal with, so we're not going to worry about our 11th order polynomials, or 9th order, sorry, polynomials. So, but we can certainly go through this process. We can figure it out. We're really hoping for zeros to pop up in that initial. That makes our ice table much easier. But we can always compute the QC value if we do need to figure out the direction of a shift.
Okay, we got our first question for participation 220 in this video. Just getting started though, a couple more videos left, more and more about ice tables. Getting fancier and fancier. If you have any questions about anything, let me know. See you in the next video.